Hi everybody, in this video I'm going to go over a problem-solving strategy for how to solve kinematics practice problems. I'm going to go over the strategy and then I'm going to do a practice problem and then we're going to do two together. Okay? So when we have a kinematics problem, the first thing we want to do is what we call sketch and translate. So that means you're going to read the text and make a list of what you're given, what values you're given. Then you should sketch the situation. And again, you don't have to be an artist, just do the best that you can. But make sure that you include a 0, a positive direction, and a negative direction. The next step is to make a physical representation. So this could be a motion diagram, a dot diagram, or a graph. It's important to make a physical representation because that will help you tell if your mathematical representation makes sense. Our third step is to represent mathematically. So we have a bunch of different equations that we could use. And so we're going to use our list of values that we came up with, along with our sketch and our diagram, to choose which equation we need to use. Then we're going to plug our numbers into the equation. And our fourth step is to solve and evaluate. So this is where we're going to solve mathematically, and then think about whether or not this answer makes sense. If you know your object is moving in the positive direction, make sure you got a positive velocity. Okay, so let's do a practice problem together, and we're going to work through all of these steps. So here's our problem. An arrow is projected by a bow vertically upwards with a velocity of 40 meters per second. It reaches a target and stops in 3 seconds. The acceleration due to gravity is 9.8 meters per second squared downwards. What is the velocity of the arrow just before it hits the target, and how high is the arrow located? Okay, so I'm going to go to my first step. I read the text. Now I'm going to make a list of what I'm given. So I know my starting velocity, or initial velocity, is 40 meters per second. I know my time is 3 seconds. And I know my acceleration is 9.8 meters per second squared. Okay. I don't know my final velocity, and I don't know my final position. When I say how high, that means I need to figure out the position. Now let's draw a sketch of the situation. So this is my target. This is my arrow. Okay. And I need a positive, a negative, and a 0. So I'm going to say it starts at the 0. I'm going to say up is positive, down is negative. So now I have to go back and make sure my signs were correct. Right, so I said my initial velocity was positive, which it is because it's moving up. I said my acceleration was positive, but it says here that it's downwards. So then I need to make that negative. Okay, so I'm done with my first step. My second step is to draw a physical representation or make a motion diagram, dot diagram, or graph. I'm going to make a dot diagram. Actually, let's do a motion. Okay, so I know it's going to be slowing down because it comes to a stop. So my dots should get closer together. Let's make this my 0. Again, this is positive, this is negative. And then for a motion diagram, we just need to add our arrows. We also need to add a delta V arrow. And remember, the delta V always points towards the larger arrows. Okay. We notice this makes sense because delta V is in the opposite direction of the velocity, so it's slowing down. All right. Now let's move on to our third step, which is representing mathematically. If we can remember, let's write down these equations. We have the equation x equals vt plus x naught. And remember, this is only for constant velocity. We have v equals at plus v naught, and x equals 1/2 at squared plus v naught t plus x naught. Okay, so these are our equations. We have VTA, okay? I know I can't use this one because it's not a constant velocity, right? Our velocity is changing, we have an acceleration. I might like to use this one, but I can't because I don't have this, and I also don't have, oh, maybe I can. Let's see. I have my acceleration, I have my time, I have my starting velocity, I have my time, and I have my starting position. Okay, then I can use this one. Let's see, can we use this one? I have my final starting velocity, my time, and my acceleration, so I can use this one too, which is great because I'm looking for both the velocity and the position. Let's start with the velocity. So I'm going to use my equation v equals at plus v naught. Now I'm going to plug in. I don't know what my v is, but I know my a is negative 9.8. Again, I'm dropping those units just for now to do the math. Make sure you remember that's negative. Our time is 3 seconds, plus our starting velocity is 40 meters per second. Let's put this in a calculator, and we're going to get negative 29 plus 40. Put that in a calculator again, and I get 10.6 meters per second. And this is my answer for the final velocity. It makes sense because it's positive, and it is slower than our starting velocity. So this makes sense. Now let's do our second one. We're going to use the equation x equals 1/2 at squared plus v naught t plus x naught. Okay. Remember, you can set where it started as anywhere. So I'm going to say it started at 0. So I don't know my position. I know my acceleration is negative 9.8. My time is 3. Don't forget to square it. My starting velocity is 40 plus 0, okay? And I made that x naught 0 because I said where I started was the 0 point. So now I just put this in a calculator, and I'm going to get negative 44.1 plus 120 plus 0. Put that in a calculator again, and I get 75.9 meters, and that is my final answer. 75.9 meters is greater than 0, so it makes sense. Okay, so here we had an example where we first highlighted and wrote down a list of our variables we were given. Then we sketched the situation, and we used a motion diagram to represent it. Then we looked at our equations that we had, and we figured out which ones we could use. Then we plugged in our values and solved. Okay, let's take a look at a second problem. Here we go. We have a shuttle bus slows to a stop to avoid hitting a deer that has darted in the middle of the road. If the bus was initially traveling at negative 13.7 meters per second and has an average acceleration of positive 4.1 meters per second squared, how far away would the deer have to be to avoid a collision? Okay, so let's start by making our list. We have an initial velocity of negative 13.7 meters per second. We have an acceleration of 4.1 meters per second squared. And we want to know how far away it is. Okay, so that's like our displacement. Okay, now let's sketch the situation. And you will see that I'm a terrible artist, but it doesn't really matter. That's our deer. That is our car, okay? So let's say that our car is initially at a 0 point, and we know that it's moving in the negative direction, so I have to make this negative and this positive, okay? And we want to know how far away this is, right? But if this is 0, then we just are kind of looking for x, our position, okay? So there we go. We have a drawing and a list. Now let's make a motion diagram. We know that he is slowing down, so our dot should be getting closer. Negative this way, positive this way, 0. And then our change in velocity is towards the bigger arrows. Okay, now let's look at the equations that we have and see what we can use. We have v equals at plus v naught, x equals vt plus x naught, and x equals 1/2 at squared plus v naught t plus x naught. Okay, so we know right off the bat we can't use this because we have an acceleration. We would like to use this, right? Because we want to find that. So let's see, we have the acceleration, but we don't have the time. We have the starting velocity, we don't have the time. So we can't use this yet. We need to find the time first. So let's see, can we use this equation? We have the acceleration. We don't have the time. We have this. Do we have the velocity? Well, we know he's trying to stop, right? It says, oops. We know he's trying to stop, and if we stop, that means our final velocity is 0 meters per second. So we actually do have that. So let's use this equation. So we have v equals at plus v naught. Again, if we're stopping, our final velocity is 0. We know the acceleration is that positive 4.1 meters per second squared. We don't know the time, but we know our starting velocity is this negative 13.7. So let's see if we can solve for t. Let's add 13.7 to both sides. Okay. And now we get 13.7 equals 4.1 t. I want you to try and solve this t on your own now, and then I'll solve it for you. Okay, let's divide by 4.1, divide by 4.1, and we get t equals 13.7 divided by 4.1. And I get an answer of 3.3 seconds. Okay, so this is my time. Time is not my final answer. So now what I'm gonna have to do is plug this back in here and use this second equation. So here we have x equals 1/2 at squared plus v naught t plus x naught. We don't know what our final position is. We know our acceleration is that 4.1. 4.1 times 3.3 squared plus negative 13.7, I think that's our starting position, yep, times 3.3 plus our starting position is 0. Take a second now to solve this on your own, and then we'll solve it together. Okay, so let's put this in a calculator, and we're gonna get x equals 22.3 minus 45.2 plus 0. Put that in a calculator one more time, and we get negative 22.9 meters. So this is our final answer. Looking back at this, we're saying this is negative 22, what did I say, 0.9? Yes, 0.9 meters. So this makes sense, right? Because it's in the negative direction, and it's greater than, it's less than 0 because it's negative. So this makes sense. All right, so that's my final answer. So again, we made a list of our variables, okay? We sketched our situation and made a motion diagram. Then we realized we wanted to find the position, but we needed the time first. So we had to go back and use another equation. We used that equation to solve for time, and we noticed that when something stops, it's at 0 meters per second. Once we found the time, we plugged back into our second equation to find the position. Okay. Now, let's do one more together, and I want you to be working on this along with me. Okay. Lance Armstrong, while cycling, has a speed of 10 meters per second. He starts going downhill with an acceleration of 1.2 meters per second squared. The descent takes 10 seconds. Determine his velocity at the bottom and how far he has traveled. Go ahead and make a list of the variables you need now. Let's do it together. We have velocity initial is 10 meters per second. We have an acceleration of 1.2 meters per second squared. We have a time of 10 seconds, and we're looking for a final velocity, and we're looking for how far he traveled, which is going to be a final position. Let's sketch the situation. We have a bicycle and a person on it. There we go. Okay. Let's say he starts at 0. I always like to make him start at 0 because it just makes you have less calculations that you have to do. And we know his velocity is positive, so he's moving in the positive direction. His acceleration is positive, so that means he's speeding up. Okay? So let's draw ourselves a motion diagram. Take a second and draw a motion diagram on your own now. So we know he's speeding up, so that means our dots should be getting further apart. Add my arrows, add my 0, positive, and negative. Now let's add a change in velocity, okay? And we know it's going this way. Great. Now let's calculate. Okay, so we have two equations. Actually, 3. When we're trying to find the velocity, which of these equations should we use? I'm going to say we should use this one. We have the acceleration, we have the time, and we have the starting velocity. So let's do that together. Okay, so we know our acceleration is 1.2. Our time is 10 seconds, and our starting velocity is 10 meters per second. Take a second to solve this on your own. Okay, now let's look at it together. We have 12 plus 10, which our final velocity will give us 22 meters per second. Okay, let's think if this makes sense. He started at 10 meters per second, and now he's moving at 22 meters per second. So he is getting faster, and he is moving in the positive direction. So it makes sense to me. Okay, now what equation should we use to find the distance traveled, or the final position? When I say distance traveled, I often just solve for final position, because if you make your starting position 0, your final position will be equal to the distance traveled. So which equation should we use here? I think we should use this one. We have acceleration, we have time, we have initial velocity, we have time, and we have our starting point. So let's do it. Okay. So we have our acceleration is 1.2, our time is 10 seconds, our starting velocity is 10 meters per second, our time is 10 seconds, and our starting position is 0. Take a second to solve this on your own now. Let's do it together. Okay, so we have, let's plug this in, we get 60 plus 100 plus 0, and that gives us 160 meters, okay, which would be your final position. Makes sense, it's in the positive direction, it is greater than a starting position, so I think this is correct, okay? So again, when we are solving these type of problems, first you want to read the problem, and I like to highlight or underline the numbers. Then I make a list of the values that are given and the values that I'm looking for. Then I like to make a sketch with a 0, a positive, and a negative. One tip is if you make the starting point 0, a lot of times it's easier to calculate how far something has traveled. Then I drew a motion diagram to represent the motion. Then I came up with my 3 equations and looked for what variables I had and what I was looking for to decide which equation to use. Then I plugged in and I solved. Thank you so much for watching this video. If you have any questions, please email me and I will be happy to answer.